Hey y'all, so here's going to be our last video in the series. It's calculating percent abundance. So what we've done is we've measured percent abundance, we've done average atomic mass, you know how to make a mass spec, you know how to read a mass spec, and now we're going to figure out the percent abundance. So this is like the hardest kind of question that I can ask you. It was similar to the one on your lab. And what we're going to do is we're going to figure out the percent abundance for two isotopes of rubidium. So rubidium has an average atomic mass equal to 85.47 AMU, and it has two isotopes. So there's rubidium 85, and there's also rubidium 87. So the mass for rubidium 85 is 84.911 AMUs. The mass for rubidium 87 is 86.907 AMUs. And so what we're going to do is we're going to use the equation that we know, which is that average atomic mass is equal to mass 1 times decimal 1 plus mass 2 times decimal 2. And so we know average atomic mass, we know mass 1, and we also know mass 2. What we're solving for is decimal 1 and decimal 2. And what we can call those things are x and y. And what we have to know about these two things, about decimal 1 and decimal 2, is that they add up to 1. Because the percentages have to add up to 100%, but the decimals have to add up to 1. So if I were to solve this for y, because I would have to use a system of equations, I could say that y is equal to, well, I would have to subtract x from both sides. Y is equal to 1 minus x. And so what I can do is I can plug in, wherever I see y, I can plug in 1 minus x. So what that would give me is the average atomic mass, which would be 85.47, would be equal to mass 1, which is 84.911 times decimal 1, which we're going to call x, plus mass 2, which is 86.907 times y, and we only want one variable, so we're gonna say that this is the quantity 1 minus x. And then what I can do is I can do algebra to solve for x. So that's what I'm gonna do. So 85.47 is equal to 84.911x plus, I'm going to distribute this to both things, plus 86.907 minus 86.907x. And then all I have to do now is combine like terms. So I'm going to combine these two things, and I'm going to combine those two things. So to combine those two things, I have to move this thing over. So I have to subtract both sides by this. And then what I'm going to get is 85.47 minus 86.907 is equal to those two things combined, 84.911x minus 86.907x. And when I combine these two, if I plug them into a calculator, I would get negative 1.437. And then if I were to combine those two things, that's equal to negative 1.996x. So how could I solve for x? Well, I would just divide both sides by negative 1.996. 996. And then that would get me that x is equal to, negatives would cancel out, this would cancel out on this side, would get me 0.720. So that would be x. So this is x, so this is the first isotope, and then the other isotope is 1 minus x. So this would be 1 minus 0.720, which is 0.280. So that means that the percentage for rubidium 85, this would be equal to 0.72, and this one would be equal to 0.28. And then these are decimals, so how do I get the percentages? Well, I multiply them by 100. So this one would be equal to 72.0%, and this one would be equal to 28.0%. So hopefully that helps. Hopefully that shows you how to do things. Again, the big thing is that, you know, we use this equation that we know. We know the average atomic mass. We know mass 1. We know mass 2. And we have to know that the decimals have to add up to 1. Then I use system of equations to say that y is equal to 1 minus x. So wherever I see y, I can plug in 1 minus x. And that lets me solve for just one variable, which is x. And yeah, and then I just plug in some numbers. I do algebra, and then I combine like terms. I get x to one side, and when I get x to one side, I figure out that the first thing is 0.72, and I get that the second thing is 0.28, and then I want the percent, not the decimal. So how do I turn the decimal into a percentage? I multiply by 100. So I get 72 for rubidium 85 and 28% for rubidium 87. If you look at the mass, it skews a little bit towards 85. 85.47 is closer to 85 than it is to 87. So that's how we know that the 85 is the more abundant of the two isotopes. Hopefully this helps.